well, I'm debating if I'll make it due past the weekend if it's long, or if it's short, I'll just make it due by Friday and give you like basically 24 or 48 hours to do it. So that is my plan, just so you guys all know. The assignments due today, so I can submit after class. What assignments? They were due on the 4th. So David, for your question here, there are no assignments, I don't think, due on the 6th. If there are, they would be due, like tonight by midnight, but I don't think, you can correct me if I'm wrong, I don't think there's any assignments due tonight. The homework assignments in Alex were due on the 4th, I believe. So yes. Okay. So I'm going to try to share this with you guys. And David, if you want to circle back to that, we can. But what do I have? Okay. Now let me know. Somebody let me know if the audio works. If it does not, we're just going to scrap this. Okay. Okay. Cool. And I think you can. I think you can submit late. You can do late submissions. I think. But ACC has those settings in a certain way, and so. If you cannot, then that means like I can open it back up for you to see the problems, but you can't, do this. But okay, somebody that if you can hear this, I guess let me know. You can hear it? Oh, cool. Okay, we're gonna play this for like a minute and a half, and you're all gonna be annoyed, and it's gonna be a great way to start class. So.
Sign, opposite hypotenuse sign, opposite hypotenuse sign, opposite hypotenuse cosine, adjacent hypotenuse cosine, adjacent hypotenuse cosine, adjacent hypotenuse tangent, opposite adjacent tangent, opposite adjacent tangent, opposite adjacent long sides of hypotenuse, and the other two sides depend on which angle you're focusing on. Pick one angle and look. There's one side that's the opposite. You can clearly see that there's also an adjacent side. Sine, opposite hypotenuse sine, opposite hypotenuse sine, opposite hypotenuse cosine, adjacent hypotenuse cosine, adjacent hypotenuse cosine, adjacent hypotenuse tangent, opposite adjacent tangent, opposite adjacent tangent, opposite adjacent.
Okay, so that was our fun SOHCAHTOA lesson for the day. Yeah, that's gonna pump everyone up for class, and yeah, this is brainwashing, Paul. Yep, you are correct. At least, they did this in my high school for me, and I did it when I taught high school. It's kind of just full circle, comes back around, right? Now we're doing it here. So, and Tristan, on a serious note, you said you're having a problem with Alex. Yeah, it's not the best. I mean, if you're having problems and it is due, like that was the night it was due, please just send me an email and I can, figure out like maybe Alex was down, or like you said, it just keeps freezing and that's very frustrating. So if you guys are having problems with Alex, just shoot me an email and I can try to, maybe give you a little extra time or whatever the case. But also I do try to give at least like kind of a week for the assignments. So for example, the assignments this week are open on 3-5 and 3-6. That's what we're doing today and Thursday. And they will be due, I think I made them Sunday night, right? So you have kind of the whole week, like after tonight, you should definitely get started on it, maybe tomorrow. And you even have, the weekend, not that that's when you want to be working, but, whenever you can fit in the time. And so hopefully, and Tristan, what I'd recommend too for that is, I mean, if it's an Alex issue, definitely contact me. But if it's a like it could also be a browser issue, or maybe your computer, you have too many things running. So I would recommend just, maybe refreshing, closing out, restarting, like this type of thing. And again, if that creates a further issue, just send me an email. But yeah, you're going to dream this, Michelle. Yes. Thank you. Yeah, this is, it's definitely interesting. Right. But yeah, thanks, Tristan. Okay. I wanted to start class with that because, I thought that would be so fun. And just to put us all in a really great mood there. That guy shares some good content. I mean, that was from 10 years ago, but, okay. Now let me share my screen here. Oh, and I will.
Recording in progress.
All right, so let me try to pull up. So these are the notes for today and actually for Thursday. And right, I kind of forget. Oh, there we go. So I know it well, and that's why I'm saying with time, we will probably have time for you to do the quiz on Thursday during class if you choose to. And the quiz will be open note and all of that. So again, if I make it long, I might give the weekend for people just to have time, and then you have to upload it as well. But if I do not make it long, I might just give you 24 hours. And especially if I give you time in class on Thursday, then I would expect this to get done, right? And also keep in mind, just you want to be checking, you guys want to always be checking gradebook. I had someone come to office hours and just said, oh, I noticed something in the gradebook here. It wasn't correct. And I hadn't synced Alex up, and so we synced and it was all good. So just keep that in mind. And let's take a look at this. I don't think I had more announcements. If I do, or if I did, I'll think of them and let you guys know. But let me just adjust my screen so I can see the chat in here. Okay, bear with me. Oh, and I forget, I have to turn it on its side. I do remember this. Yeah, okay, much better. Cool. And I have posted, so when you see on Blackboard, if it says like notes from this day updated or notes, I'm trying to post them from each day, but if we don't finish, like, so today we might finish all of this, we might not. So if we don't finish, I might just put updated and not the date of the notes, or I might add a new and add it again, and it's the final version and it just repeats a little bit, right? But lately I've just been updating. So when we had like one page of notes or a few pages left, I just updated it from the previous class. But you should have access to all notes that we've seen so far. Okay, awesome. So now we're talking today. I mean, not SOHCAHTOA, right? Even though I started class on that high note, but maybe we'll need that again later. So we're talking about rational functions today and inequalities. And so a rational function is going to be something like this, function f, where you have a fraction and you have something like p of x over q of x, where p and q are just polynomials, and q cannot equal 0, right? It would be a bit silly to have like x squared plus 5 divided by 0. Like that doesn't make any sense, right? So what we're going to notice here, and this is just an example. However, we'll kind of take some notes and talk about it. So, okay. So the first things first, when we have a rational function, we have what's called asymptotes, right? So we have a vertical asymptote and a horizontal asymptote. And looking at this graph, we can see here, I mean, maybe I'll label like X and Y axis, and the dotted lines so these dotted lines, right, are the horizontal and vertical asymptotes. And basically what's going on here is the X and Y axes are basically shifting to a new place. And consider that as like the new axes, right? And so that's what these asymptotes really represent. And we'll be talking a lot about that today. So this one here is the horizontal asymptote. And it's, in this case, it's at y equals, let's see, we're assuming these are by 1. So like -1, -2, -3. So y equals -3. We'll just assume these are all like 1, 2, 3. It's very tiny, but you get it. And so this is a horizontal asymptote of y equals -3. And then here we've got the vertical asymptote. Oops. And this is going to be at x equals, I think it's 2, right? Yeah. At x equals 2. Now, what we notice here, so when we're given an equation like this, and if we were told what this was, it's pretty hard to graph, because if you graphed a bunch of points, you'd have maybe like a point here, then a point here, then a point there, and you'd be like, oh, is it a line going down? But then you'd have a point over here. So you might just get a little bit confused graphing it just by points. And so when we're given this type of function, we first look at the asymptotes, and then we say, okay, the graph in these new axes, the graph has to either be approaching the asymptote, or possibly it crosses over if it's a horizontal asymptote. For vertical, it always is approaching. So let's start with the vertical. We'll notice that so I'm going to put arrows on the ends of all of these. Okay, that one's not perfect, but we'll notice that for the vertical, we can see here that as x, and this arrow is going to mean approaching, but as x approaches 2 so we can approach the vertical asymptote from both like the left-hand side and then the right-hand side, right? So we can approach these from both sides. So we're starting with the right-hand side. Maybe that's not as natural, but coming from the right-hand side, we can see, and we write this like this: as x approaches 2 from the right, we put a little plus there. Y is going up. See how it's going up to infinity. So y is approaching infinity. And then similarly, it's still going up to infinity. So if we look at this one, as x approaches 2 from the left, we see that y also approaches infinity. And we just want to note that, these little guys, this just means like from the left or from the right. And you're going to see that below in the chart. So maybe I should highlight that. So this notation, or maybe I'll just do this and this, means from the right and from the left. But it will never equal 2. So this equation, whatever it is, we don't know what it is just yet. But whatever this graph, the equation of this graph is, it's never going to equal 2, because that's the vertical asymptote. So that probably means that in the denominator, there's something like x minus 2 somewhere, because we can't have 2, and it's like a divide by 0 error. So they're both approaching infinity. Now we take a look at the horizontal asymptotes. And there could be lots of different things going on here. But one thing I do want to point out is that at some point, this point right here, it doesn't matter what that point is, but I just want to note that it crosses the horizontal asymptote, which seems a bit weird, right? Like it crosses it and then comes back. It's always going to approach it in some way, but it potentially could cross this asymptote. The reason that this can happen is, what this means is if we call this function f of x, right, the f of x that we had at the beginning. So I'm going to say f can cross a horizontal asymptote. I'm just going to label this as HA. Or can cross the HA, or can cross, maybe I'll say can cross the horizontal asymptote at, in this case, y equals -3. If f of x equals -3 is a real number. When we set this function equal to -3 is a real number. So if it's a real number, that means that's an actual point on the graph. We're going to cross this asymptote, but the asymptote still exists, right? It's still there. And we'll learn how to figure that out later, how to find the horizontal asymptote. But if it's not a real number, then it would not cross there, and maybe it would have done, maybe it would have just gone here and not cross that line, right? If that was not the case. So maybe we can note wait, I don't know if I wrote this clearly, or maybe I said it clearly, but when I say if f of x equals -3, I mean if x is a real number for this. Hopefully that made sense. Like if you solve this for x, so if f of x equals -3 is a real number when solving for x. Because obviously -3 is a real number. We're good to go. And f, we could set it equal to -3 and say, sure, it's real, but you need to solve for x. So when you solve for x, this is the case. And I won't make a note if not. If not, it just means it approaches the asymptote. You don't have to worry about it. But we still can say, so notice we still have this guy here and this guy here, right? We still approach it on either side. But what we can say now, instead of saying from the left and from the right, we would just say as y approaches -3, x approaches this value. And let's see, well, here, let's write this. So on this side, we have, and actually, or we're still going to start with x, I guess. Sorry. So we're going to do exactly what it says down here. X approaches infinity and -infinity. We're going to see what happens. So what we have here is as x approaches -infinity, y approaches -3. Y is always approaching -3. That's the horizontal asymptote here. So we can see, like, because remember, this is the x-axis. So as x goes on and on to -infinity, we can see here that this is approaching, getting really close to -3, but it only equals -3 at that point, like right there, right? The rest of the time, it's just approaching. Okay. Now we have this side where we say, oh, I don't know why that made it a straight line. That was weird. Where we say as x approaches positive infinity, y approaches -3. So again, if you were graphing this or if you had to explain it, it's not going below that. It's restricted. And so looking at this graph overall, there is a minimum because we see x, or they go up to, y goes up to infinity at x equals 2, right? From the left and the right. But if you look below, if you kind of look below, like just this level right here, or even this level right here, there's no, nothing there, right? There's nothing below. Oops, I'm on the other side. There's nothing below this for the function. So that just means this function actually has a minimum value for y. And then the range would be anything greater than that. Okay. So now this little chart basically explains what we just did, right? So the notation is x approaches c, and in this case, that was our asymptote. So we had 2 from the right, but it will not equal c, and then it approaches from the left, and then we just look at what y is doing. And then for the horizontal, we say x approaches infinity, right? And then approaches -infinity. And what goes on. We're looking at the behavior, really, of this rational function. Okay, so let's look at this example. Oh, hopefully, if people need to still see that, let me know, but hopefully I'm not scrolling too quickly. So now we want to find domain and all vertical asymptotes of this function. So like I said, typically, actually, domain and the vertical asymptotes are related, because for domain, we want if we have a fraction, we do not want 0 in the denominator, right? So our domain, it means it cannot equal these numbers. But then our vertical asymptotes are actually related to those numbers that make the denominator 0. So let's take a look and rewrite this a little bit. So my h of x here, I can factor the top and the bottom. So, geez. Okay, we're right here. We're good. So the first step here is going to be factor. So I'll have x plus 1 and x minus 1. That's what x squared minus 1 factors to be. And then in the denominator, I notice I can take a 4 out and also an x. So I factor that 4x out. So I'm basically dividing each term by 4x. And then I have x left in the first one minus 1 left in the second one. So if I'm finding just domain, so I'm focusing on domain first. So, and you always want to find domain before canceling any terms. Because I know some of you might see this and be like, yeah, we can cancel that. Like, that's great. But before you do that, you definitely want to find the domain first, because even though we're canceling it, going back to the main function, this value still, like x equals 1 cannot be in our domain, because in the main function, we would get 0, divide by 0. Well, 0 over 0, I think, right? So that's just not a good thing. What's going on with that, right? So to find our domain, in this case, and I'll write it the way that we did the other day in that like interval kind of notation, or no, bracket notation or something. So x such that x is not equal to 0 and x is not equal to 1. And I know this just because I would set 4x equal to cannot be 0 and x minus 1 cannot be 0. And then I would just divide by 4 and add 1 to both sides, right? So that's how I found that. So there's our domain. It's the first part. Now the fun part is we get to cancel these and keep solving. So we can cancel these. How beautiful. And we're just left with x plus 1 over 4x, right? So this is our simplified function. So this is nice. Now, I want to note that for vertical asymptotes, we're going to find all VAs after canceling. Okay, so these are just two important things to note about the domain and the VAs and when you want to find them, right? So now we can take a look at this and we can say the vertical asymptote, and this is going to be, is when the denominator equals 0. And so 4x equals 0, x equals 0, right? Because we can just divide by 4 and get that. Or maybe I should. Okay, so then I'll leave my other answer here, VA at x equals 0. And these are our answers for that problem.
Would there be like a hole or something at 1?
Yeah, so this is great. So what's happening here is there is a hole at 1. And so if you were to graph this, because when you cancel terms like this, so William brings up a good point, when you cancel terms, what's happening is there's just nothing that's there. You can't, okay, sometimes you could fill in the hole, but in this case, we would not. The way you would fill it in is you would write a piecewise function and say, okay, h of x, you would say something like, it's this when x is not 0, and then it's 2 when x is 0, or something like that. And you would just plot that when x is 0. But I mean, we're not doing that, but yeah, so here there would be a hole. So if we were to graph this, and again, I mean, I'm not going to be perfect here, but at wherever, like, so again, say the function came in here then there'd be a hole at 0, and then say it kept going, whatever it looked like, something like that. So that's what this graph would look like. And maybe instead of leaving a wrong graph, I'll just write, I'll write a little note. We'll say canceling these terms means there is a hole in the graph. Okay, cool. All right, so that was the vertical asymptotes, right? So now we're looking at horizontal and slant. Okay, this might get a little more tricky, and hopefully everyone's good with this. But we're going to try to make it so that we all remember what the heck's going on, and it will be okay. So we're going to look at horizontal and slant asymptotes. The degree of the numerator, this happens when the degree of the numerator, which we're going to call just n, oops, I didn't want that, we're going to call it n, equals the degree of the denominator plus 1, which we'll call, oh my goodness, which we'll call n. Oh, something happened there. Okay, n plus 1. And that will be the degree of the denominator plus 1. Okay. So I think I just am calling it m and n. I don't, did we do that here? No, we didn't say. We're just going to call it that because then we can refer to the degree, whatever number that might be. So to get this, we do people's least favorite thing, and we have division of polynomials to find the slant asymptotes. So when you want to determine a slant asymptote, you basically have to do polynomial long division. And good, Michelle, you like it. It's fun. Yeah. I have to say that most days I like it. There are days when, my math brain isn't as turned on and this can be difficult. So if
Lost your audio. Is that just me?
Yeah, we can't hear you.
Can't hear you.
can't hear you. All right, can you guys hear me now? Maybe my headphones.
Yeah, yeah.
Yes.
All right, the headphones stopped working. That's fine. Okay, so we'll just go without them tonight. So we have this to determine the slant asymptote. We have f of x is 2x squared minus 8x plus 8 over x minus 3, and x minus 3 is what we're the denominator is always what you're dividing by, right? So in this case, it's called our divisor, right? So I'm gonna set this whole thing up, and let's try to make it nice. Maybe I'll shift it. Yeah, okay. Okay, I have my long division here. I know that x minus 3 is going to go here. Okay, you don't need the parentheses around it maybe, but x minus 3 goes there. Then in the inside, I have the numerator. So 2x squared minus 8x plus 8. All right, one second, that dog. Okay, so when we divide this, and I'll label these for us, but like this is the divisor, and here we have the okay, the dividend is less important, so maybe I don't know if that will confuse people, but that is called the dividend. And then what's most important is going to be our answer, which is the quotient. That's like the answer to, and then we'll have a remainder, right? So let's check this out. So if you remember long division, great. If you don't, what we do is we take the first term here, and we say, okay, what do I need to multiply this by in order to cancel out, to get it to be equal to that first term? And there are other ways to think of this, but that's kind of how I think of it. So I'm going to say, okay, well, I know this is 2x squared. this is x. If I multiply by 2x, then that gets me 2x squared, right? So I'm going to take this 2x and I'm going to multiply this whole thing by 2x and write it below here. So I get 2x squared minus 3 times 2x, so 6x, right? And I'm putting it in parentheses because we have to subtract it. So what's going to happen here, and this is how we continue the long division, right? So, and maybe I can note that 2x, x minus 3, that's what goes there. Okay. And if this is too confusing, I apologize, but hopefully you can organize it in your notes that it makes sense. But so now what we do is we subtract. So you could distribute this negative, say plus and negative, and make this plus, and then we just add straight down. So these first two cancel. You should always, always, always cancel that first one. Then I get negative 8x plus 6x. So this gives me, I'll keep this, negative 2x. And then there's nothing to add with the 8, so I just bring that plus 8 down. And we're going to work our way towards the end to get rid of this, right? Okay, so now I think, okay, I have negative 2x. So I have this, and I have this. So what can I multiply by to get rid of that negative 2x to make those the same? And it's going to be just negative 2. So then in my answer in the top, I just write minus 2. And then remember, I'm going to say negative 2 times x minus 3. And that's what I'm going to write in the parentheses again here below this. So it's going to be negative 2x plus 6, I think. Yeah. And so again, I'm going to, I put that in, oh my goodness, whatever happened, undo, oh geez, cancel, yeah, okay, cool. Whew. Okay, so I'm going to subtract this again, and add going down, and remember this is what I have here. So when I do this, I'm just gonna have plus a positive, and this is going to become a negative 6. Okay, so I can cancel these two x's out, or negative 2x plus 2x cancels out. And then 8 minus 6 is only 2. So I am left with 2. And the reason I know, so this is going to be my remainder. The reason I know that I'm done and it's my remainder is because I can't take a non-fraction and multiply by x to get 2. I'd have to divide by x and then multiply by 2, right? That's not going to work. We're not going to do that. So what's left here, up here, this is my quotient, which is basically the answer we were looking for. And so we can rewrite f of x in this form with the quotient and the remainder. And I'm going to show you, well, and here's how we'll do that. So the answer, or the new function, I don't know what you want to call it, is going to be the quotient plus the remainder over the divisor. And that's why the dividend, it's good to know that word, but not as important because it doesn't come up again. So I'm going to use this right here to rewrite the function up here. Okay, so let's give that a try. So this is going to now be my quotient, so 2x minus 2, plus my remainder, which is 2, divided by divisor, which is x minus 3. And then what happens here, so we rewrote the function using long division, but the whole point of this was to try to find a slant asymptote, right? So what happens here is that this piece, this determines the end behavior of the function, like whether it's approaching infinity, negative infinity, 2, 5, I don't know,
it determines that. And it represents the slant asymptote. So the slant asymptote is at y equals 2x minus 2. Right? And this last piece, you're also probably wondering, like, what the heck does this do? Well, this, what happens here is, and this is going to be always true, well, always true of your remainder, that as x approaches plus or minus infinity, so if I take an infinitely large number or an infinitely large negative number, I get 2 divided by some really, really, really big positive or negative number. And if you just think about, 2 over 10, 2 over 100, 2 over a million, that number is getting smaller and smaller, and it is approaching 0. So as x approaches plus or minus infinity, this fraction approaches 0. Or you could rewrite 2 over x minus 3, but this is the extra piece that makes our function kind of unique and not just a line 2x minus 2, right? But it actually goes away. The reason for the slant asymptote is because as the numbers get bigger and bigger, the function approaches that slant, because it starts to become, this fraction basically goes to 0, and the function just becomes 2x minus 2. And so there's our asymptote there. So if we were to graph it, if you had really, really big numbers, that line 2x minus 2, this function is going to look more and more like a line, but it's not actually a perfect line. It's approaching 2x minus 2, but because infinity is not like a real number, this 2 divided by x minus 3, it'll always equal something. It might be 0.0000001, but it's not going to equal, like, actually equal 0. Okay, so that's kind of an example of a slant asymptote. And then horizontal maybe is a little bit, is it okay to divide the other way? I'm not sure what you mean, but divide the other way. If you got the same answer as me and you just did a different method, I would say, yes, Michelle, this is okay. If you got a different answer and you did something different, then this isn't going to work. So for example, if you swapped like this and this, that's not going to work unless you're like secretly dividing it the same way we did, but just looking different, if that makes sense.
Would there be a hole at 3 on that, or how would that work?
So at x equals 3, there's not a hole. It's a vertical asymptote.
Vertical asymptote. Okay.
Yeah, good question. But we weren't, because we were just finding the slant. I mean, we'll eventually get to one where we find all of them. But yeah, for now we're just focusing on this. And Michelle, if I didn't answer your question, just let me know. But yeah. So Michelle, if you're using a different method, this is perfectly fine. I just prefer this method here. Can I use long division for this? Yeah. Isn't this long division? Is that not what we did? So Jakob, correct me if I'm wrong, but
I don't know. I just think that is, you're writing for the polynomial, just numbers without the x's.
Oh, I see. So yes, you just have to make sure, Jakob, that you add the x's back into your answer, right?
Yeah.
But yes, you can absolutely use that like little kind of trick like for this. And then German asks, how do you find the y-intercept? So in this case, there might not be one, right? But to find the y-intercept, you would substitute in just 0 for x, right? And in this case, then there would be. So we can write that out just for fun. Oh geez, that's a highlighter. So let's not do that. So y-intercept is when x equals 0. So f of 0 is just 2 times 0 squared minus 8 times 0. That's all 0. So just 8 over 0 minus 3. So -8/3. And that's how you find the y-intercept. if that makes sense, hopefully. Yeah,
When it comes to, I guess I'm just confused because isn't 2x minus 2 a linear equation? And
Yes,
how would there be a
so-
vertical
okay,
asymptote?
so what, okay, so 2x minus 2 is linear, but remember our main function here was this. And this is not linear. So what's happening is this whole thing turns into let's see.
Oh, I see. So we're also kind of finding the vertical asymptote at the same time.
Yes, yes. Yeah.
Okay.
Yeah. So we're separating it up, yeah, into basically a linear, because if you look at the degrees, you have like 2, and then in the bottom you technically just have 1. So when you divide, if you look at the main terms, when you divide those out, it's just x, like x squared over x. It's a linear. It's going to look like a line because we're dividing here, but it's
Right.
actually a rational function. So it's got weird like asymptotes, and it's got like holes maybe, or it's just got weird things going on, and it's not a perfect line. And then
Okay.
David says synthetic division greater than polynomial division. Yeah, see, this is where we would disagree. So I like polynomial division better, but that is maybe just because I teach it. I don't know.
Wait, sorry, could you repeat that?
So David said in the chat that synthetic division, that's so my bad. That's what they've been talking about this whole time. That the long division that I think Jakob and Michelle were talking about is they're actually using synthetic division, which is a way, it's a method for you to you can take out the zeros, the x's, and just write numbers. Now I have to say this does not always work. If you have a way that it works for you all the time and you've always gotten to work, that's great. But I'll always do polynomial division, even if it's something easy. But there are ways that synthetic division, if you make one tiny mistake, it just messes you up and you're not going to get it right. And you're going to be so confused, like, no, I did division, I did it right. But this is just something for all of you to keep in mind. Those of you that are fans like David and Michelle and everyone, if you prefer this way, again, I'm totally cool with it. Just please make sure you're doing it correctly, and it only works when you have a linear function in the denominator. So I don't think we'll ever see anything else. But like, let's say you had, if you had something like totally crazy, and you had, like 3x to the 4th plus 6x squared minus 2 or 35. I don't know, something weird. And then you had like x to the 3rd minus x squared plus x plus 1. I don't know. If you had something like this, and again, like, this is not a real example, because do not try this. This is not going to work. But if you had something where the degree is so big, I don't know a way that synthetic division works. So this is why I like polynomial division better, just because polynomial division will never fail you. You can still set this up and still try to solve, right? Whereas long division or synthetic division could fail you potentially. Maybe there's a new way. Oh, and Jakob said something on YouTube. Maybe there's a new way that I don't know. Oh yeah, thank you. So Jakob sent this YouTube video of synthetic division. If anyone is interested, click that link and get that SOHCAHTOA song out of your head. No, I'm just kidding. Yeah, so okay, Dave, yeah, you'd have to make a lot of zeros for the, yeah, so that's just not fun, right? But I'm gonna get off this sidebar before I confuse people. But yes, so great questions. I love it. And good discussion, although I would reverse that inequality that you sent there, so in the chat. Okay.
Okay, I have a quick.
Oh yeah.
Okay, so is the answer just going to be y equals 2x minus 2, or is it 2x minus 2 plus 2 over x minus 3?
Oh, sorry. Okay, yes. I never really gave the answer, right? So the function, this function f is equal to this whole thing, but the slant asymptote is equal to just this. So the answer to the question, Veronica, is y equals 2x minus 2. That is it.
Okay, thank you.
Yep. And later, I hope, or I don't know when, and if we're not doing this today, we're definitely going to do it Thursday. We'll look at an example like this we'll find the horizontal asymptote, the slant asymptote, the vertical, we'll find all of it and we'll graph it together and just take a look at what that really looks like. And again, if we don't do it today, I will definitely have problems like this for Thursday. Okay.
Wait, one more quick question.
Yeah,
So
Michael.
that's a slope intercept form, basically, right? Why
Oh yeah,
is
this is what, yeah. So this right here is y equals mx plus b. So like if we were to graph that, it's just a line, right?
yeah, it's just like, but
Yep,
is the
it's-
quotient always going to be in that sort of, combination of number, like a 2x minus 2, or, like a number x plus or minus another number?
Yeah, so it should always be in that form, your slant asymptote. It could just be x plus 1, or it could be as complicated as, 3/2 x minus 5/6. Like it could, I mean, granted, we won't probably see as many fractions, but you can see something like that too.
And that depends on the point that was made at the beginning about the numerator is equal to the degree of denominator plus 1. That's why.
Oh yeah. So the reason we have a slant asymptote, like I said, is exactly because these degrees, that the degree of the numerator is 1 higher than that of the denominator. Yeah.
Thank you.
Yeah. Cool. Okay. All right. So let's take a look at now finding just horizontal asymptotes. So this happens when, as you see here, that when the leading terms, or we're going to look at the leading terms that they're going to dominate for large values of x. What this means is that we're going to look at an example where, so we first looked above at an example where m was equal to n plus 1. So m was a little bigger than n. So now we're going to look at an example where if we're talking like, oh, I keep doing this. I want the pen. Where m is the degree of the numerator, and let's let n be the degree of the denominator. So in this case, if we look at this, well, maybe I should call these these are two separate problems, right? So if we just look at f, this here, m in this case, there's no x in the top, so it's 0. So it's less than n because in the denominator it's 1. And so what we want to do here we have larger degree in the denominator, right? Which we hadn't seen yet. So what's going to happen here, the nice thing about this is whenever this happens, you have a horizontal asymptote at y equals 0. Nothing, there's no, so the answer here is going to be HA is at y equals 0. And it's solely because, we're going to look at why. It is because the degree in the denominator is bigger, right? So because of this, it's just at y equals 0. If you just remember that, you don't ever have to worry about it. But what's happening here, and the reason this happens, is because if we focus on the leading terms or the largest terms, so this 2 in the top stays, but the -1, if I have infinity plugged into x, infinity minus 1 is still going to be huge, right? It's still going to be real close to infinity. So we can kind of ignore that -1, and we look at this 2 over x, and we say, what's going on here as x goes to really big numbers? Well, kind of like before, I don't remember when, but when we looked at this right here, as x goes to plus or minus infinity, the fraction goes to 0. This is the exact same thing. So we're going to say here, as x goes to plus or minus infinity, this whole fraction, maybe I'll say 2 over x minus 1 goes to 0, approaches 0, right? And 2 over x approaches 0, but x minus 1, like I said, not making a big difference. So we're focusing on these leading terms. We're going to also look at the leading terms for the next one. This will be more helpful, because if you just memorize that when m is less than n, it's HA at y equals 0, you're good to go. That's kind of how, even though that's maybe not right, that's how I've always done it. Like I knew why, I learned why, and then I was like, not important anymore. All I need to know is that, I mean, okay, it's important. I shouldn't say that. But yeah, so we've got y equals 0. Now we look at the h of x here. And for this one, I see it's a 2 and a 2. Okay, so this m equals n. They're same degree. Same degree in the top and in the bottom, in the numerator and the denominator. Same degree, right? So for this one, you can basically ignore everything else except for the terms with that highest degree. That's what they're talking about, these leading terms. So we can basically ignore everything else except x squared over 4x squared. We can ignore these for now, and we will only look at the leading terms for end behavior, like what's going to happen, and for this horizontal asymptote. So if I only look at that, then I'm left with, I'm just going to focus on this. This is y equals x squared over 4x squared. So what's happening here is, I mean, these guys are canceling out, right? If I simplify that, that just cancels, and I'm left with, do not mistake this for 0 over 4. This is not 0 over 4. This is 1 over 4, right? Because there's a 1 in front of that. So don't forget about that. So this means that there's a horizontal asymptote at y equals 1/4 for this equation. So the cool thing, there's kind of 3 rules, right? When m is bigger than n, you either have a slant, or actually you're usually going to have a slant. You do the polynomial long division and you see what's going on. When m is less than n, it's just HA at y equals 0, right? Yeah, just like this second one. Then when m and n are equal, right? When these two degrees are equal, you take the highest degree. So if it's squared, you take those x squareds and you just look at the coefficients, the leading terms coefficients, and you divide them. Maybe it's 2 over 1, maybe it's 1 over 4, whatever it is, that is your horizontal asymptote. So there's kind of these 3 rules. Now, if you are thinking, okay, I get if they're equal, like, so we have like 3 situations. I get if they're equal. I get if m is less than n. Well, in this case, m specifically was n plus 1, because if it's any bigger, it just, when you do long division, there'll be no remainders. It'll cancel out, and it's kind of, there'll be no horizontal asymptote. It'll just be a normal graph, and you won't have to, I mean, for the most part, unless you do long division, unless you cancel things, but you would cancel in the numerator and denominator, and then maybe the degrees would be the same or something. I don't know. Is it in VAs where if m is greater than n, it equals 1? I'm trying to think. I don't think so, because vertical asymptotes is just when the denominator equals 0. Oh, but if the numerator's, no, yeah, that's not. I
I can't remember what the rule was, but I feel like there was something in my last class where it would equal 1, but I
yeah,
can't
and there is. I know what you're talking about. I know what you're talking about. It might be the case that what you're saying is correct if there's no remainder.
Okay.
I will check on that, because
We didn't do slants in that class, so.
right. See, so okay, so they might have also been giving you been giving you like on purpose things that came out to just 1 because they were giving, so they said whenever m is greater than n, because I think that's what I taught in high school as well. Or even at my class. Yeah, I think that's what I taught before. So I'm just gonna write a note to check m greater than n if y equals 1. Okay, I'll check that and mention it on Thursday.
Okay.
If I don't, just like ask again, because I'm gonna look it up after class, and so
Okay.
I'll write it down somewhere. Okay, but yeah, but I'm pretty sure, and that's, so the slant asymptote, I mean, it'll happen when m is n plus 1, and but if you don't have a remainder, well, then it's just y equals 0, and something else is going on there, and something cancels out, or I don't know, something like that. Okay, so now we have our horizontal asymptote, slant asymptote, vertical. So now we can match this description, okay, which it's going to say here, but this is exactly what we were just talking about. So let's see if we can match this up correctly. So m is less than n. Okay, so m is the degree of the numerator, n is the degree of the denominator. That's how we've been defining it the whole time. When m is less than n, we can see from just above, but that should be just y equals 0. So that should be b. And if you want to, like, match it to here, feel free. If m equals n, this is where you take the coefficients. So this is where you take, okay, horizontal asymptote at y equals a, and it's non-zero. So this is where you just take those leading coefficients. So this is going to be c. Let's get here. Now, the m equals n plus 1 is what we were just talking about, and this is the slant asymptote. However, I'm so interested that potentially, if there's no remainder, it might just be y equals 1, and you're in the classes that Veronica or Victoria, both of them, were kind of talking about. It might be the case that in that class they were doing that on purpose. They were making no, like, you could do the long division, but then you just get 1 or something like this. But I will look more into that. This will be, we will confirm that on Thursday, or maybe even at the end of class. Maybe we'll take a 5-minute break or something. I can look in the book. And then, so what they are saying here, if m is bigger than n plus 1, which is what I was saying before, what will happen is there's not going to be a horizontal or slant asymptote, because the numerator is so much bigger than the denominator that it'll cancel out. And if you did the long division, there'd be no remainder. There'd be, it's just canceling out. And so it's almost like a normal graph. We don't see this like too often. This is usually when it simplifies to not be a rational function. Oh yeah, okay, Victoria, I see what you're saying. Okay, cool. And so I think the easiest way to like look at this type of stuff is to just get down to it and complete some examples. So looking at this problem here, they want us to do everything. They want us to get the intercepts, x and y, get the asymptotes, find horizontal, vertical, slant, whatever's there, graph them as dashed lines, then determine the direction on the ends. So this is where we would look and say, oh, as x approaches infinity, what's happening here? As y, approaches this number, what's happening here? And basically, when you determine that end behavior, you can sketch your graph. It might look a little funky, but you can sketch it. So then we're gonna determine any crosses and then plot some points and finally sketch a curve here. So this is gonna be kind of a big few graphs here. Let's begin. Okay, so first things first, I see f of x is this function here. I'm gonna focus actually it's the same function we just did, so we're just graphing it. So I'm actually gonna copy it from above. Let me do that, right? It's it's the same one as this right here. So I'm just gonna take the 2x minus, I'm not gonna redo long division and all that. I'm just gonna take the 2x minus 2 plus 2 over x minus 3, and I'm gonna write that out. So we're saving ourselves a little bit of time here. Equals, let's do this one equals 2x minus 2 plus 2 over x minus 3. Okay, so this is what it equals. We know this from above. So from above, we're not just magicians and we made this up and said, oh, look how smart I am. Okay. So we also know if we focus just on the denominator, this tells us x minus 3 cannot equal 0. So x cannot equal 3 in our domain, but that means our vertical asymptote is at x equals 3, right? I'm starting with asymptotes. I could go back to intercepts. So I'm not going in order here. So I apologize if that bothers me. But then we know from the work that we did above that this here represents the slant asymptote. And it's y equals 2x minus 2. I guess I would say that. And then let's get the intercepts and we'll get the intercepts. Okay. The intercepts in this. Let's divide these a little bit. So we'll do intercepts. Okay. So for the intercepts, if you want to just make a little chart, because maybe this will help you, you know that you can plug in 0 and solve for y, and then plug in 0 for y and solve for x. So f of 0, somebody asked this on, maybe they were looking ahead, somebody asked this on the previous page. So f of 0 is going to be, I can just plug in 0 squared minus 8 times 0 plus 8 divided by 0 minus 3. And remember, we got -8/3, I believe, right? So 0, -8/3 is our y-intercept there. And the x-intercept is going to happen when we set this thing equal to equal to 0. So we say f of x equals 0. So that means that 2x squared minus 8x plus 8 over x minus 3 has to equal 0. So the nice thing about this, when we set this equal to 0, we can basically ignore the denominator, because if I multiply both sides by x minus 3, it would cancel. It would be 0 on the one side, it would cancel on the other side. So I can cancel this. So basically we're just solving for 2x squared minus 8x plus 8 equal to 0. And this is a nice equation because we can factor. Somebody just asked a question. What is the horizontal asymptote? There is none. There's a slant instead. So you typically do not have, so in this case, we have the slant asymptote and the vertical. You do not have a horizontal asymptote and a slant asymptote at the same time. You kind of have one or the other. That's why they're grouped together, typically. But yeah, so in this case, the HA is the slant asymptote, right? Hopefully that answered your question. Okay, so now let's finish factoring this. I can take a 2 out of everything, and I get x squared minus 4x plus 4 equals 0. And then I think, okay, let's see. You should be able to factor this, right? So I think it's just x minus 2 times x minus 2. So I could put squared, which means there's only one. You could do the quadratic formula if you couldn't factor, but in this case, it factors nicely. So this means that x equals 2 is my x-intercept, and because it happens twice, so this little 2 means that this point occurs like 2 times. And what that means is when we graph it, it's going to bounce off of that point instead of crossing through the x-axis. So that's what this means. So maybe I'll make a note of that. So I'll say the multiplicity, and that's what this is called. Oh, I wrote that weird. No. Okay, the multiplicity of x equals 2 is 2. So, so because the multiplicity is even, or it's 2, again, it's going to bounce off of that. I don't really know how else to say it, but so the graph, I'm going to just put it in quotes, and you'll see when we graph it what I mean by bounces. You can adjust as necessary if you think it's a different word is better. Okay. So last thing we want to just talk about here is I have the slant asymptote, and remember how I said a horizontal asymptote, if you have a horizontal asymptote like y equals 1, if the function is real, if the x value is real when I set that equal to 1, then it crosses through. And if it's not real, then it just approaches, right? It doesn't cross over. This is the same thing. So if we want to ask ourselves, let's see, maybe we want to ask ourselves, does f of x cross the slant? And it will cross only if the remainder, so that remainder that we found here, only if the remainder can equal 0 for some x value. Okay, and in this case, we have 2 over x minus 3 equal to 0. Well, the only way, and this is like a question mark, the only way that this could happen is if the numerator, which is 2, equals 0, which it's not. So no. So does it cross? No, it's not going to cross this slant asymptote. And so now let's start to kind of graph everything. They recommended what you do, but we'll start with the vertical asymptotes as dotted lines. Let's do something. Oh, and they labeled this. Okay, so this is like 3, 6, 9, 12, -3, -3. So they went by threes for whatever reason, right? That's fine. So my vertical asymptote is at 3. So that's here. And I'm just going to draw my nice dotted line there. My slant asymptote, because it's a slant, if it was horizontal, we could just kind of sketch it. But because it's a slant, I'm going to plug in a few points so that I can try to get it as accurate as possible. So I'm looking at 2x minus 2. So if x was 0, it's 0, -2, which maybe would be like here. If x is 1, it's 0. So, okay, maybe I should plug in bigger numbers. If x is 3, or we're not going to have 3 here. Or yeah, we can. If x is 3, what's that? 6 minus 2. Okay, so maybe for this, what we want to do is just do something like this and say 0, -2, 3, what was that? 2? Because it's 6 minus, yeah, so 3, 2. I don't know, somewhere around there. And then 6, 12, 10, I guess. 3, 6, 9, 10, 0, somewhere here. Okay. All right.
Is it 3, 4?
Oh, what's up?
Is it 3, 4?
3.
Y equals 4.
Oh, 6. Yes, you're right. That's why it didn't look right. Okay, thank you. Good. Oh, clearly I'm losing it here. Okay, so 0, -2, 3, 4. And you could have, like, I see some people saying, oh, 2, 0, 1, 8, 1. You could have plotted other points, but because we went by threes here, I wanted to plot points that are further apart so I can try to, figure this out. But yeah, 3, 4 makes way more sense. And so I'm gonna get rid of that. And if it's 3, that's much better. I was like, my line's not going to look so good. But okay. So now we can kind of make a dotted line. And this is our slant. So maybe we should label these. Like this is the vertical asymptote. This one's the slant asymptote. And now what we want to do, but last but not least, is plot a few points. So we want to plot some points, at least 1 point in each interval defined by the X and Y intercepts. Oh, I guess we could plot the intercepts as well. So this was 2, or maybe this was 2. Okay, so the intercepts were, and you could think of these like ordered pairs, were 2, 0. So maybe that would be like here. And 0, -8/3. So that would be -8/3 is like -2.66 something, right? So, so yeah, my graph, this is going to be hard. I need to adjust kind of what I've done here. I did this too large. Maybe I need to erase all of this. Okay. We're going to try this again, just to make it look maybe.
-2, -6.4.
Yeah, it's -2.66, right?
6.4.
6.4. What do you mean? What?
Um,
I'm just graphing 0, -8/3. So right now I'm just graphing this guy here, 0, -8/3.
alright.
I just didn't have room on my graph to make it look nice, because it's supposed to go like right there. Right.
So you are not graphing the whole expression?
No. I was just graphing the X and Y intercept. We are going to graph the whole thing. I just was doing the X and Y intercept first. And so now I can clearly see, okay, what's going to happen here? I know my graph does not cross the slant asymptote. And based on these 2 points, the 2 points here and here that I just graphed, I know that this has to approach the slant asymptote. And I know, remember that bounce thing I was saying? It's going to hit this 2, 0 and bounce back off and approach the asymptote again. So I know that's a part of the graph, but I'm missing another part of it. So what they recommend when they say plot points here is I'm good on the left, on this left-hand side of the x-axis. I'm good. I don't need to plot any points there because I have this guy. But I'm missing something over here or maybe up here. I don't know where it is, but I'm missing a piece of this graph, right? So what we want to do is we want to maybe plug in a value like 4 or 5 or something like that for f and see what happens. So if I substitute in f of 4, we'll try that. I'm going to get, okay, 2 times 4 squared minus 8 times 4 plus 8. And you could just do this in a calculator, I guess, 4 minus 3. So that's 1632 minus 32. Oh, it's just 8, I think, 8 over 1. You can check that, but I think it's just 8. So that's nice because now I know 4, which is like right there-ish, right? And then 8, which is like somewhere in there. It's like about right there. So this tells me that, again, I'm not crossing my slant asymptote. So because I have a point inside this little kind of V right here, because I have a point in there, I know that my graph is just going to approach the asymptotes and curve really close to it. You can plug in more points if you're not sure. Like if we plugged in 6, we'd get, oh gosh, 36 times 2, so it's 48. You'd get something along the lines of like maybe you'd get between like 10 and 12 or something. And so you could plot that and see, okay, I'm approaching my asymptote here. And you could even plug in 3.5 to see what it's doing on the left side of that. But this is a good gauge of your graph. You basically want to look at points that are in, this area, like look at points, points on the x-axis, and then plug those in to your original function and figure out what y is and see where these points are. Oh yeah, and Michael, thank you. It's 10.67. So if we plugged in 6, it's almost 11, right? So if I was to graph that and I'd say, okay, 6, and then maybe it's this point right here, right? And you would see, okay, it's above our slant asymptote. So now I kind of have an idea of what the graph is doing. So this is a trick, and these are tricky ones. Like you're not always, you might just get one that has a vertical asymptote and it's kind of easy and it's not really that complicated, right? But these are definitely tricky problems to graph. Okay. All right, so let's check out the next one. So again, I'm going to start by looking at, or we could start with the intercepts this time, maybe, just because I kind of messed up that order last time. So if I'm looking at the x and y intercepts, let's look at that. And maybe I should kind of separate this problem. Got a lot going on. Okay. So my x and y intercepts, I want to figure out when x is 0, what's going on, and when y is 0, what's going on. Except I think in this case, when x is 0, y is also just 0. So we just get 0, 0. Those are the x and the y asymptotes. So maybe that's a bit boring. But we'll plot some other points after. So intercepts, we're good to go. These are the intercepts. And we can just note that f of 0 equals 0, right? And then I see here, so if I focus on the denominator, x squared minus 4, if I set that equal to 0, this is like x minus 2 and x plus 2, or vice versa, right? So so I'm going to have 2 vertical asymptotes here. So I have a VA at x equals 2 and x equals -2. I'm going to have 2 different vertical asymptotes, right? Okay, and then I see in the chat, and I'll kind of circle, this was the x and y intercepts. And then I saw in the chat we have says horizontal asymptote is 2, and that's correct, because I would look at, I see squared and squared, so I focus on this right here, I ignore that -4, and I can see that the HA is going to be at y equals 2/1, which is just because this is like a 1, right? So you take those leading terms and you just get the coefficients, and then to figure out, does it cross? So does it cross y equals 2? What we have to do is set f of x equal to 2 and say, is x real? Fx equals 2, or let's see, is x real when f of x equals 2? That's the question we're asking ourselves. So let's look at that. So I have 2x squared over x squared minus 4 equals 2. So I can solve this by just multiplying both sides so I have 2x squared equals 2 times x squared minus 4. And I'm just going to keep doing this. I'm going to say 2x squared equals 2x squared minus 8. Then I would subtract 2x squared from both sides. But then these cancel. I get 0 on this side and I get -8 on this side. and this is false, right? 0 is not equal to -8. So this does not work. So no, this is not true. This does not cross. And so now what we want to do, the last kind of thing, is just to find some extra points. So we just want to find, so maybe we'll extend our graph here, and we just want to find some points. And it looks like, yeah, it looks like they went by 1 here. Yeah, they went by 1. Okay. I'm just always like, I mean, normally we can make our own graphs, but it's nice when the graphs are just here for us, right? So you could plug in like 1 and -1, but I want to kind of get a range of like numbers. So I'm gonna do maybe 3 and -3. And again, you could plug in different values or more than me, but we'll start with these and see, you know, if we need to go anywhere else. And you can't plug in 2 and -2 because those are the asymptotes, right? So actually, and what would help you to see this is here. If we graph, let's see, what did I do? Okay. If we graph the vertical asymptote and the horizontal asymptote, we plot them. Let's take a look at what that's going to look like. So I have a vertical asymptote at 2 and -2. And then a horizontal also at 2. So looking at this, and I know that my graph goes through, let's do here. I know the graph goes through 0, 0 because of this point right here. So I know that I should be able to figure out, what's going on kind of in the middle. But what I don't know is what's going on here, or is it there or there? I have no idea, right? So I want to substitute in values for X here and here. So you could pick 4 and -4, or 3 and -3. I just picked the smallest that I could, right? But yeah, so we'll do 3 and -3. They are, I think, going to be fractions, you know, fortunately or unfortunately. So for f of 3, I get 2 times 3 squared over 3 squared minus 4. So this is going to be 18 over negative, 9 minus 4, so 5, right? 18 over 5. Okay, so this is just 18 over 5, which if you, as a decimal, it's like 3.6. And then when I plug in -3, the same thing's going to happen because all of these are squared, right? These are both squared. So if I changed that to be a negative, nothing's going to happen, like negative, negative, negative. It's still the same thing. So it's still 18 over 5 or 3.6. So this is helpful for us. And we know that it doesn't cross the horizontal asymptote. So now we can graph these. We can say, okay, let's plot these points. I have 3, okay, 3.6, so that's like somewhere in there. -3 and 3.6 is somewhere in there. And I know, so when I think about what's going on, every single place here is gonna approach whatever asymptote it's closest to. So if I'm on this left-hand side, so when I'm looking like here, I know that it's gonna approach the asymptote here and approach there. I know approach and approach. And I know this is not going to go up because that means it crosses the horizontal asymptote. And we know it doesn't do that. So it must go down. Okay. So these are kind of the shapes that I have in mind. And so now I can sketch them. And it does not have to be perfect. If you want it to look much nicer, you could plot like 3 more points in each section, and then you would have a really nice graph. But I don't even think, well, the graphing calculator, at least that I have, wouldn't graph something like this very nicely. It would look a little bit chaotic. But I think the newer graphing calculators do a pretty good job. But again, it's hard to see. Like it's good to know, kind of what's going on here. It's hard to tell if you just graph this in your calculator.
What kind of calculator do you have?
Like the old graphing calculators, like a TI-83 or something. So I don't know if I don't even know what students use now, what is available now. I have not bought a calculator in a really long time. And I actually only use scientific calculators right now. So, but I will say, with the internet, Desmos has a really nice graphing calculator, and it would probably graph this nicely. So maybe I spoke too soon. Desmos would do a good job. Okay, so I think, well, we're gonna do this next example. I think it likes at least 3 points. Yeah, so Michelle said at least 3 points. Yeah, you probably. I mean, especially something like this, you want at least 3 points just because what the heck is going on, right? So I'm doing the minimum here, but I think if I was to be graphing this on my own, I also might, just to check myself, I might graph 2 more points in the sections or something, just to check it out, make sure it looks good. Okay, so we're gonna do this last example 7 on the next page, and then we're actually gonna just finish the rest of this these notes on Thursday, because this is the last of the sections before we review for your test. And again, like I said, I might give some time on Thursday for a quiz and also some questions, like homework questions. Oh, geez, homework questions or whatever. Oh, how do I get out of this? Okay. Or whatever else people like, if the grading is wrong or whatever, feel free to ask me. Oh, and a little announcement I wanted to make, so hopefully everyone's good with that, is just that my office hours, I don't remember if I said this or not. Right now they're 5 to 6, like before class in the Zoom room. I'm gonna kind of change that start time to just 5:15, just to give myself a little time to commute home from my previous class, and because today it was cutting it tight, and then I was cooking dinner, and luckily nobody showed up right at the beginning, but it was not good. So yeah, I'm gonna start them at 5:15, and a few minutes before 6, maybe 5 of, I'll head to this class. But I will, I apologize for that. Originally, I think I only had them on Tuesdays, but I'm learning Thursdays have been more popular. So I'll have them both days, but just for the 45 minutes. Okay, I wanted to make that announcement before I forgot. Okay, so if time permits, which time is permitting, so we're gonna graph this last one. And again, it's like there's a lot to look at here, but let's start maybe with let's start with the intercepts. I guess let's do that. So let's do intercepts. So I always just like to make this chart because it's like clearly lays out the points for me. So if I substitute in 0, like in all these places, right, I'm pretty much just left with, like, everything cancels and I'm left with what's at the end there. So it's going to be 5/6. And then to find out my X values here, if I set this whole thing equal to 0, then I only need to focus on the numerator. I do not need to focus on the denominator because the numerator has to be 0, not the denominator, right? So so I'm going to just set x squared minus x minus 5 equal to 0. Now I look at this and I say, does this factor? And maybe I would try a few things, but maybe the reason this is the time permitting one is because it does not factor nicely. We are going to use quadratic formula. So, we did long division today, polynomial division, quadratic formula, all the good stuff came out today. The SOHCAHTOA song at the beginning of class, we just had a great day. So keep in mind that, like, 1, this is A, -1 is B, and C is going to be -5. So we have negative B plus or minus the square root of b squared minus 4ac all divided by 2 times a. I'm going to simplify this a lot because like here, this 2 negatives cancels to be a positive. So that gives me 1 plus or minus the square root of 1 minus 4 times 1 times negative 5 is plus 20 over 2. And so these will be 1 plus the square root of 21 over 2 and 1 minus the square root of 21 over 2. And if we get these as like decimals, which when I say if, we should, because I have no idea what those numbers would be. They should be, I think this is about 2. I'm just rounding to one place. If you want to round to multiple, that's fine. There's no specification here. And then this one's, oh, I'm doing a squiggly. What's that? Negative 1.8. So yeah, so these, these are going to be our x-intercepts. So I'd say you could fill it in here if you wanted, negative 1.8. And we could even graph it. I think, what do they go in twos here? 2, 4, 6, 8, 10. Yeah. 2. Okay, so they went by twos. I was just curious. So now I'm going to focus on the denominator for my vertical asymptotes. So x squared minus 5x minus 6 equals 0. Luckily, we can factor this. They made this nice for us at least. So this factors into x plus 1 and x minus 6. Yeah, I think so. So x is negative 1 and 6. So these are our VAs. VAs are at negative 1 and 6. And then focusing on the horizontal asymptote, I have n equals n here, right? So, I have m equals n here. So I'm going to focus just on these coefficients, and there's just 1 over 1. So this might be the case, I think, where actually, no, this is not the case where it's just y equals 1, but I am still going to look into that and why we teach that when m is greater than n. But in this case, my horizontal asymptote, so let's see, if I just focus on these guys, we're going to say HA is at y equals 1. And then if we want to say, does it cross? Maybe I should have written this somewhere else. Does it cross? Well, we have to set f of x. So remember, the question is x real or is the statement true when f of x equals 1? That's our question. So maybe this might confuse you, but I'm going to write it over to the left here. So we have x squared minus x minus 5 over x squared minus 5x minus 6 equals 1. So this is what we're questioning. Is this true or does this work? Is it possible? And so to do this, I'm going to multiply both sides by the denominator, right? So I'm going to say, okay, multiply this by x squared minus 5x minus 6. Multiply this by x squared minus 5x 6, right? So that it cancels here and here. And then I'm just left with x squared minus x minus 5 equals x squared minus 5x minus 6. Okay. So I can, from this point, I can subtract x squared from both sides. Those will cancel out. I could add 5x to cancel that, add 5x, and add 5. I'm doing all of this at once. So if this is confusing, you can do one step at a time, but these cancel. I'm left with 4x over here. This cancels, and I'm left with equals -1 and x equals -1/4. So yes. So the answer is it does cross because in the last case, we got something like 8 equals 0. Okay, 8 does not equal 0. The x is all canceled. That's fine. But that just means it never can happen. In this case, we get x equals -1/4. That's cool. If we got 1 equals 1, 2 equals 2, then it also would cross. It means it would work. But typically if it works, if it doesn't work, you'll get a false statement. And if it does work, you'll get x equals some number. So it is going to cross, and the point is at -1/4. So we could even add that to or create another little xy. It's going to be when x is -1/4, y is 1. It's going to cross at that point. Okay, so now we can kind of start graphing everything, and then we'll plot like an extra point or two. So first, I'm going to start with our asymptotes. We have at -1, or this is by 2 though, right? So -1, there's a vertical asymptote. 6, vertical asymptote. And then y equals 1, so that's this in here. Okay, and I can clearly see like 3 panels here. So now I'm just going to start graphing or plotting the points that we had. Let's do like this. So I'm going to plot, and again, I'm going to plot all the points that we found. So we found this point, we found these points so far, right? So first I'm going to plot 0, 5, 6. So 0, 5, 6 is like slightly less than 1. So oops, I'm in the first. So it's like here somewhere. 2.80 is maybe like there. -1.80 is maybe, there-ish. And then -1/4 1. So -1/4, oops. -1/4 1 is like here. Or even less, something somewhere in there, right? This is really teeny tiny, so it's a little bit hard. But remember, we cross the horizontal asymptote, that one point. I already plotted it, but we do not cross it again. So from the points that I just have here, I know that this is going to do something like that. Okay, so I'll plot that. So from this point, I'm going to approach the asymptote here and approach the asymptote there. Then from my next set of points, this is a weird set, but I think we're going to approach over here, then curve up and approach over there, but don't cross it again. You don't cross the vertical. We're only crossing the horizontal. So I'm going to have something like this, and then like a weird swiggle like that. And then the last thing we're going to have, I don't know what the heck's going on over here. So I just need to pick a number that's bigger than x equals 6 and plot it. So it could be 8, it could be 7, it could be whatever you want to do. I picked 7, but you could also pick 8. I was just, again, finding the smallest number. So f of 7, I found it was about 4.6. So what that means is that at 7, I have about 4.6, which is like somewhere in there, right? And now I know, okay, there's a point. I know it's not down here. I know it's got to be up here approaching my asymptotes. So I go here. And there's your graph of this pretty complicated function. And again, we're gonna finish these notes on Thursday, this same set. I will post these to Blackboard tonight. You do have a homework assignment on 3.5 and 3.6. It is due not till Sunday, I believe. And yeah, Joseph says, when is our first test? The first exam is next Thursday. So I am going to try to get a trig quiz up here back on SOHCAHTOA probably for this Thursday. Yeah, and Victoria, question of the day. Yes, let me find what I wanted to do. So think about your question of the day today is going to be your favorite travel spot or favorite vacation. And you can whether it's not going anywhere, whether it's a certain location, like if you haven't traveled much, that's okay. But if you have, I'm just curious. I like to read about it. And I'd say my best vacation, I like Hawaii. I saw that, and I like staying home too with my dogs, obviously. But I actually got to go to Italy for sort of my honeymoon, and so that was probably my best vacation. Now we're kind of like, all right, no vacation's going to top that. Should we just stop? We'll just stay home, right? Save money, stay home. Yeah. No, but I'm kidding. But yeah, so favorite vacation spot, go ahead and type that in the chat, or you have 1 more minute to think about it. And this Thursday we'll most likely have a short quiz. It will be online though, and open note. So I mean, just individual. So please don't call each other and ask the answers. And definitely make sure you show your work. And yeah, we will finish these notes on Thursday, and then start reviewing for our first exam. Please check your grades in Blackboard, check your attendance, make sure I'm doing it all correctly, because it is a lot for me to read through. And while I enjoy reading all your answers in your chat and checking everything, it is a lot. So just please make sure, double check me, make sure it's right. But yeah, any questions before it is 7:45. So those of you that, are tired, yeah, some people are like, yep, goodbye. Okay.